Done.
Okay.
YouTube is live?
Yes, sir.
Oh,
Bye bye. Good afternoon and welcome to the 12th lecture of the lecture series on radar meteorology, jointly organized by South Asian Meteorological Association and Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. Welcome back again and good afternoon east of Nairobi and good morning west of Nairobi who are staying. And actually, we got a very good response in the last midterm test. More than 150 participants, attendees have actively attended the test, and even the more than 100 people is having more than 75% of attendance all together. So everybody took that test very seriously, and we got good response and good. I think 100% pass almost. Thank you very much for taking this seriously. And without delay, I invite Professor Someshwar Das, sir, Secretary Sama, to propose the welcome address.
okay. Thank you, Dr. Vilas. AVM Professor Ajit Tyagi sir, President of SAMA, the Chairman of the lecture series on radar meteorology, Dr. Devendra Pradhan, today's distinguished speaker, Dr. Pandithurai, our organizing committee members, Dr. Vilas, Dr. Palomi, Dr. Divyapakash, and others who have switched off their videos, Rakesh, Rijoy Revelo, and of course from Myanmar, Deputy Director General Dr. Kya Luin U. So you are all welcome to the 12th lecture of this radar meteorology lecture series. As you know, as announced earlier, of course, today Speaker Dr. Pandithurai probably, he joining just for his lecture. He might not have joined the previous lectures. So for his information, and those who are in YouTube, those who are just joining today, I will like to tell you that in this lecture series, about 1,200 people from 48 countries registered for this lecture. As you know, this is a continuation of our efforts on capacity building of the people of South Asia and the member countries of the non-aligned movement. Many of you know that the first online lecture series was conducted on atmospheric physics for 4 months. That was followed by a hands-on training on the WRF modeling system for 3 weeks. And that was followed by, again, a 5 months lecture series on satellite meteorology. All these lecture series are jointly conducted with some of the academic institutions. Like the first lecture series was conducted jointly with SRM Institute of Science and Technology at Chennai. The second one on the WRF modeling system was conducted jointly with the CDAC, the Center for Development of Advanced Computing in Pune. The third lecture series on satellite meteorology was conducted jointly with the Birla Institute of Technology and Science at Ranchi, Mesra Ranchi. And this is the fourth lecture series on radar meteorology, which, as you know, is being jointly conducted with ACARR, Advanced Center for Atmospheric Radar Research at Cochin University of Science and Technology. This lecture series will go on almost up to 5 months because there are 20 to 22 lectures in our schedule in this radar meteorology. Also, the speakers, all the speakers of this lecture series are very senior people, distinguished scientists or professors from different institutions. As you know, we had announced earlier that there will be a final test also. We had just conducted last Saturday, as mentioned by Dr. Avilas, the midterm test so that let the participants know how much they have understood and what is their level of understanding so far. And as already mentioned by Dr. Avlas, we had a good response. Many people attempted the midterm test. As he said, I think more than 100 people attempted the course, lecture series, or 149 to be precise, 149 people. And many people got good marks, above 80%. The highest is 83%. And many of them are above 75%. So, as we have announced earlier, we shall give certificates then for those who will qualify or score in the final test, above 85%, like outstanding grade, above 80%, excellent, and so on. So please be serious and try to attentively attend the lectures, not only which is being telecast live, but also you can go through the lectures on the YouTube, because all the past lectures are archived on the YouTube also. So you can attend that lectures. And we mentioned also earlier that those who will have more than 75% attendance, they will get some special certificates. So please be regular so that you can get also the attendance certificate. For your information, I can tell you that almost like 34 people have 100% attendance so far. And those who have attendance above 75%, I think there are about 118 people. So we have good number of people who are attending the lecture series live, and we encourage you to attend further all the remaining lectures also live as much as possible. The details of this test results as well as the attendance percentage will be shared by Dr. Avilas shortly, hopefully in this week, to all the participants. So please be regular on that. And also, as you know, at the end of each lecture, we have a question and answer session. So please write down your questions in the question and answer box, and it will be taken up by our moderators and it will be answered by the speaker. So enjoy the lecture and have a good day. So Avilas, over to you.
Thank you, sir. Now I request President Sama AVM Aditya Risab to deliver the presidential address.
Thank you, Abhilash, and Professor Someshwar Das has given overview of our lecture series and the test conducted. It is very encouraging to see that we have a good attendance of large number of participants, and they have appeared in the exams, have done well. So it speaks good of the organizers who are conducting these. They have speakers who have created interest and imparted good knowledge about the radars, right from the basics to the advanced topics, which are now we are in the process of taking lectures, like today's lecture on cloud and precipitation radars. I'm really thankful to Dr. Pradhan, the chairman of this organizing committee, Abhilash, and all other organizing members. And of course, the strength of our lecture series is with our eminent speakers. So today we are lucky to have Dr. Pandithurai. I think radar meteorologist, researcher with a wide experience in all type of radar applications, from cloud research to the cloud physics, radiation and precipitation part. And he has been, you see, spearheading the various activities promoting the radar part. You see, the ACARR is one part, but then we have a higher altitude lab at Mahabaleshwar. Then the Testbeds is coming up, has come up in Bhopal, near Bhopal. And of course, the network of radars in Mumbai. So as a project director, he has been doing a wonderful job in setting up these facilities, which will further promote radar-related operational as well as research work. He has wide experience both in the universities as academicians also. He's been visiting professor at Maryland and also in Japan University. So great, and operational and research part. So he'll be imparting very important aspect, because essentially radars, we make them used for the precipitation measurement also very extensively. In fact, that provide in the remote areas where we don't have other measures, radar complements that, and we are creating a daily rainfall map using radar, satellite, and the rain gauges. So all this is a very important set of observations. So today's lecture will cover this aspect, and there couldn't have been a better speaker than Dr. Pandithurai for this topic. So thank you. Make best use of it. There is a question answer session. Please ask questions. You can follow it up on the YouTube, as Dr. Somesh has mentioned, and get benefited. So once again, thank you, Pandithurai, for accepting today's giving lecture today, and to all the participants, make best use of it. Thank you.
Thank you, sir. So now I request Mr. Rijoy from ACARR to introduce, though Pandithurai sir is not need any kind of introduction in the radar community. He is actually my teacher when I joined in IITM as a junior scientist, and then we were colleague there. And after that, he was helping us with as a project steering committee member for our ACARR Advanced Center for Atmospheric Radar Research, and then he is also a member of our SAMAS radar meteorology course. And for the audience, I request Mr. Rijoy to introduce the speaker.
Thank you, Abhilash sir. I am extremely glad to introduce Dr. G. Pandithurai sir, who is presently working as Scientist G and Project Director of Atmospheric Research Testbed of Indian Institute of Tropical Meteorology, Pune. He completed his doctoral research at IITM and obtained his PhD from University of Pune in 1998. He did his postdoctoral research work in Department of Atmospheric and Ocean Sciences, University of Maryland, USA, in 1998 and 2000, and as a visiting professor in the Center for Environmental Remote Sensing, Chiba University, Japan, during 2008 and 2009. He has been holding various scientific positions at IITM and contributing to aerosol, radiation, and cloud physics studies using aircraft and ground-based observations. He took a lead in establishment of the High Altitude Cloud Physics Laboratory at Mahabaleshwar in Western Ghats during 2012. In High Altitude Cloud Physics Laboratory, he aimed to understand how aerosol physical and chemical properties affect the cloud microphysics and precipitation using long-term measurements. Currently, he is spearheading the establishment of atmospheric research testbed in central India and establishment of urban radar network for over Mumbai metropolitan region. He published about near 175 research papers in peer-reviewed journals and guided 10 PhD students. Thank you, sir.
Sir, please. Pandithurai.
Yeah. Thank you very much, Dr. Tyagiji and Dr. Someshwar Das and Dr. Pradhan and Dr. Abhilash for kind words. So I'm sharing my presentation. Please confirm whether it is visible.
It's visible, sir.
It's in full screen mode. Or...
Please to the full screen. It will be.
Yeah. Now it is.
Thank you.
Oh, okay. So thank you very much. So I think last so far 11 lectures have been over on this radar meteorology course, especially in our atmospheric science. So we need to understand various processes which are relevant to atmospheric convection and its interaction with the radiation, humidity, surface fluxes. So all these processes are still not very well represented in models. Hence, so still the research is very active in these areas. So, and if you look at these sketch, so you can see there are various processes and cloud types ranging from stratocumulus, cumulus, congestors, and cumulonimbus, and ice clouds like cirrus. So the clouds is a major uncertainty in the in our understanding and in climate change. In climate change scenario, with the increase of temperatures and with increase in emissions and particulate matter, so the clouds are perturbed, and these clouds have it's a major resource for fresh water and hydrological cycle. So if we can better represent these cloud processes in our numerical models for weather prediction and climate projections, so we'll be able to understand our Earth system better. And radar plays a major role in observing these uncertain variables like precipitation and clouds. And when we say radar meteorology, which is the study of the atmosphere and weather, using radar as a tool. So the weather radar sends pulses of microwaves, and it gets back how much is getting reflected by the targets in the atmosphere. In the atmosphere, targets are mainly drops, raindrops, cloud droplets, rain, snow. So there are different hydrometeors. And benefits of these weather radars are it can see the echoes from meteorological and non-meteorological targets. We can detect and measure the velocity of targets and thus indirectly the wind velocity. It can make a graphical presentation of basic reflectivity and velocity products. And we can also derive the value-ordered products for graphical presentation. Such products are the result of retrievals from the raw data sets. There are limitations also, which is the range is limited by the curvature of Earth, and we need a clear line of sight blocked by terrain or man-made objects. So, and ground clutter, the non-meteorological echoes, interference from other radiators, and the attenuation of beam as it passes through the echoes. And this is the entire microwave spectrum. And as we mentioned that we have to go from the micrometer sized cloud droplets to millimeter size raindrops and to centimeter size the hailstones. So we need to cover like 4 or 5 orders of size range from cloud droplets to hailstones. So one frequency of radar may not be sensitive to all these different types of hydrometeors. Generally, for precipitation studies, we use mainly S-band, C-band, X-band, and Ku-band. So they are called as precipitation radars. And W and Ka band are radars or cloud radars. So if you look at this spectrum, so the top axis shows the frequency in gigahertz. If you see from right side, S band, which is from about 3 gigahertz, and C band is about 5 gigahertz, X band is about 10 gigahertz, and the attenuation, the transmittance is getting decreases in especially in higher frequencies. So it is mainly due to the attenuation. So the cloud radars, which are mainly between Ka and W band, so there will be considerable attenuation. So but they are sensitive to the micrometer-sized cloud droplets. The precipitation radars, which are in centimeter wavelength, so which may not be observing the non-precipitating cloud echoes. So we need to use millimeter wavelength cloud radars. So again, the previous lectures speakers must have covered. This is the radar equation for weather radar. The radar reflectivity of a storm is independent of the radar. It is truly a property of the storm. It only depends upon the number and size of the raindrops in these storms. And these are some of the typical radar displays when we look at the radar's display screen, which is plant position indicator. So it will map like display with radar its center, and in all directions you will see if there are a storm, and if you get reflectivity, it will be represented like this in PPI display. And again, the scanning pattern is, so it will, if you can see that there is it changes the elevation angle and scans the entire azimuth to scan the complete volume of this storm. Okay, so this is how the radar makes slices and build the complete volume of this. Then the other type of scan the radars use is the range height indicator. If you want to study a storm's vertical structure, so you can point the radar to the particular storm and take the height cross section of the storm. So again, the rainfall is derived. Rain intensity is derived from ZR relations. So this also must have been covered already, but so just for completion's sake, I'm just saying that the precipitation is from a non-polarimetric radar. So you can convert this radar reflectivity to a hydrologically useful parameter. There are several empirical ZR relations are used to convert radar measurements to rainfall. For example, over orographic region or for convective rain, stratiform rain. So there are different ZR relations are in use. So again, if you want to improve the rainfall estimate from the radar, there are some methodologies that if we have very accurate rain gauge measurements from the ground that are at some specific points within the radar field of view. So these measurements are also can be used to adjust the radar data at these points so that both systems give the same rainfall values. So then these correction factors can be applied to the radar data around these points to improve rainfall estimates. However, in inaccessible regions like the orographic mountains, so we cannot have ground-based measurements in many places. Okay, so radars plays a major role in such inaccessible regions so that you can get the rainfall over the mountainous regions. So the in-situ observations are nearly impossible in complex terrains and in inaccessible regions. So radar plays a major role, and also it can give you a better spatial and temporal resolution of a rainfall estimate. So this is, I think, third. Then I think the course coordinators are planning a separate polarimetric radar lecture. But however, I have some brief information. So in conventional radar, the reflectivity and velocity measurements only are possible. So it cannot give you the hydrometeor classification, etc. Whereas if you want to study the hydrometeors and all, so we need to use a polarimetric capable radars. So because as you all know, raindrops are not always spherical. and it can take oblate shape when its size increases. So if you can use both the horizontal and vertical polarization, this you can better understand the oblateness of the droplets, and also uh, this will be used to better understand the microphysical processes like hydrometeors and other information. So from the dual polarimetric radar, in addition to the reflectivity, so we can also get differential reflectivity, which is the difference between horizontal and vertical polarization reflectivities, and the phase measurements, which is like it can give you information about the attenuation. When there is a higher rain intensity, there could be higher attenuation, so which could be used to uh, have better estimate of rainfall. So also the correlation coefficient between the both horizontal and vertical polarization returns, so which can give information about the symmetry of the hydrometeors and regularity. In addition, the linear depolarization ratio also can give information about the shape of the hydrometeors. So the benefits of dual polarimetric radars, we can get an improved accuracy of rain estimates, so better flash flood detection, and the ability to differentiate between heavy rain, hail, snow, and sleet, and improved detection of non-meteorological echoes. So if you want to understand the differential reflectivity, you can look at if there's a ratio of the reflected horizontal and vertical power returns. Okay. So in this figure, you can see there are different types of drops, hydrometeors. So from top, you can see if the raindrop is about 2.7 millimeter, the ZDR could be about 1.5 dB. If raindrops below 0.3 mm, so which will be like spherical droplets, so the ZDR will be 0. The size is, if size increases, you can see that the ZDR also gets increased. So for a raindrop of about 8 millimeter, you can see it looks like a oblate donut shape. So you can see the ZDR could be about somewhere 6 dB. So it mainly depends on the median shape and size of hydrometeors. So the shape of the hydrometeors can be inferred, and the presence of larger droplets also can be indicated. So for hailstorms like a 9 centimeter hailstone, it looks like a spherical, so its the ZDR could be a 0. So ZDR is estimated from the reflectivity of a horizontal and vertical channel and the logarithmic. So these are examples of different ZDR values. So ZDR greater than 0, which represents the horizontally oriented mean profile of hydrometeor. So if it is less than 0, it represents the vertically oriented mean profile of hydrometeor. ZDR is 0, which means it's nearly circular mean profile of hydrometeor distribution. So then again, the other parameter, correlation coefficient, which is a measure of the correlation of the horizontal and vertical backscattered power within a radar sample value. If there is a small diversity in hydrometeors within the sample volume, so the value could be about 0.9621. If there is a large diversity in hydrometeors, the correlation coefficient could be somewhere between 0.85 to 0.95. For non-hydrometeorological targets, the correlation coefficient will be less than 0.85. So the area of weaker returns is characterized by lower values of correlation coefficient, which also can give an indication that these could be non-meteorological targets. So whereas the area of high reflectivities fall in an area of high correlation coefficient, indicating hydrometeors are all the same size. The areas of higher reflectivity are characterized by lower values of CC, indicates likely the mixed precipitation. Then the other polarimetric important parameter is specific differential phase. It represents the difference in phase shift between horizontal and vertical polarized returned energy due to forward propagation. Here, the horizontal phase shift is greater than the vertical phase shift. So if you look at here, so if phase shift, you can see the all three diagrams having different types of hydrometeors. So in the bottom panel, you see that there are large number of raindrops. So higher rain intensity. If there is a higher rain intensity, the phase shift will be much larger at horizontal polarization, so than the vertical. So this indicates high value of KDP indicate area of heavy rainfall with more liquid precipitation. So these are immune to even the calibration, which is very sensitive in the non-polarimetric radar. So as in the introduction, it was mentioned that so the high altitude cloud physics laboratory in Western Ghats. So to understand the cloud and rain processes, especially the orographic cloud and precipitation processes, there were two radars deployed in the Western Ghats in Mahabaleshwar, which is 100 kilometers from Pune in Maharashtra, India. So this is the radar location at which both these frequency of both the radars, both cloud and precipitation radars were deployed. And you can see the specifications like frequency, which is the X-band radar, which is at 9.5 gigahertz, whereas K-band cloud radar, which is at 35 gigahertz. The wavelengths, corresponding wavelengths also you can see. So both were using a magnetron and klystron transmitters. So the peak power is in X-band radar, it's 200 kilowatt, and whereas in the K-band, it is 2 kilowatt. And these are the other technical parameters. The antenna diameter for X-band radar is about 2.4 meter, whereas the K-band radar antenna diameter is about 1.2 meter. And if you look at the minimum detectable signal capability, so for K-band radar, it's somewhere about minus 45 dBc at 5 kilometer. So it is sensitive so that it can even look at the, you can sense the cloud drop, micrometer sized cloud droplets. So this is the precipitation climatology, where in India, if you see that the Western Ghats is one of the heavy rainfall region. So to understand this orographic precipitation process, we deployed both cloud and precipitation radars. So I will show some of the results from here. So this point is where the center is the radar location. So you can see in all four directions, about 125 kilometer, the radar can detect the storms. These are the one monsoon season statistics. So what you notice is this is the Western Ghats Mountains. So where you see the more number of cells, convective cells. And this is the leeward side, what you see from the right-hand side. So are you able to see my mouse movement arrow?
Yes, sir.
Okay. Okay. So so what you see here, this region is the leeward side and this is the windward side. So you can see clearly in the windward side, there is abundant of congestus type of convective cells. And over the mountainous, the high peak regions, you can see more cumulus clouds. And whereas in the leeward side, you can see the deeper cells were more frequent over leeward side. So that's what you can see over the orographic regions, because what happens is the southwesterly moist laden winds. So when they come, it hits the Western Ghats mountains. There is a forced ascent which leads to the condensation, and so the lot of collision coalescence, and it leads to warm rain processes over Western Ghats windward side. So still the models are having trouble in to represent how the convective cells and they diurnally with the time how they evolve. So what you can see from observations is that so you can see in the local time of about 15 hours. So 14 to 14 hours, you can see the congestus peaks. So whereas the deep convection, which is given in blue column, which takes about 2 to 3 hours lag to peak. So for such a transition, so we need to have some mid-tropospheric moistening and heating by these congestus type clouds. So that's an important process here. Also, when you look at the monsoon core zone, in addition to the Western Ghats, if you look at the monsoon core zone, so here, so this is the correlation between the core monsoon zone rainfall and all India summer monsoon rainfall. So you can see a high correlation between these two. And if we can improve the process understanding over this core monsoon zone region, so we will be able to better represent the precipitation or cloud convection processes in core monsoon zone. Also, this core monsoon zone in India gets influenced from a lot of low pressure systems which forms during June to September over headway of Bengal and moves towards the northwestern side and brings heavy extreme rainfall events over core monsoon zone. So radars plays a major role in understanding this in understanding cloud and precipitation systems. So to understand these processes, IITM also established a atmospheric research testbed in central India, wherein we deployed a dual polarization C-band Doppler weather radar here. And in addition to Doppler weather radar, there were other facilities also deployed in this central Indian region. So this is the circle, what you see here in this map. So that is our location where the research testbed is established to understand the convection processes. So these are a whole lot of instrumentations were set up in this site to understand the feedbacks from convection, precipitation, and land atmosphere interaction processes. So there are further in coming years, there'll be some more additional instruments will be added here. So these are broad objectives of the atmospheric research testbed, which Dr. Tyagi mentioned in the introduction. So idea is to have in the tropical region to have an in core monsoon zone. We need to have better understanding on land atmosphere interactions and convection cloud and processes. Also, these observations could be used in in a model, single column model, and some intensive observational campaigns are being conducted here, so that the modelers can test it in single column model, and in turn they can improve the tune, modify the cloud processes, and later they can improve it in a three-dimensional model. That's a idea behind this observational facility. So this is one of the such a passage of a typical convective storm. So over the radar domain. So like how the convection organizes, it starts like you can see like starts like a scattered convection, then it gets organized into like a squall line and brings in a heavy rainfall over the core monsoon zone. Also, radar data plays a major role to better understand the convective organization. So if you look at the large-scale features, so this is what you see is from the 30 minutes satellite brightness temperatures. So you can see there's the cyclonic circulation, which is moving northwestwards and westward. And whereas if you want to understand the mesoscale features, so we have a high resolution 6 minutes radar reflectivity. So we can see that the full radar domain can get filled with this entire storm. So you can see that this is one of the extreme rain event happened in 22nd August 2022. So about 293 millimeter. So this kind of extreme rain events could be test cases to study the radar echoes to different types of rain types, different rain types such as convective, stratiform, and mixed, and also we can measure the degree of convective clustering. So that's the idea. The rain types are classified using an algorithm with different cases, so that you can say, okay, this is what fraction is different, what fraction is of convective type and stratiform type. So if you look at the examples, scenes of convection, so the top row shows the radar observed reflectivity at different times of the day during the event. Initially, it started like isolated shallow cells. Then you can see a small clusters of convection with a limited stratiform. Then at 1559, you can see there's a squall line associated with the stratiform area. Then the entire radar domain, you can see widespread stratiform. So people try to use this radar data set to compare it with how well the model is able to capture. So these are some studies which currently going on to understand. So these data sets could be valuable resource for testing the models and improving and tuning the models. And also, we can use this to study the rain types. So as I said, so what fraction of occurrence is from the convective rain and stratiform rain? In this case, this heavy extreme rain event case is considered. The peak rain time is from peak rain time, you go back 24 hours this side and the other side. So about 2-day event. Okay. So what you notice is here, initially, the convective rain was predominant. Then later the stratiform rain, convective rain decreased, and the stratiform rain is more. So this is how you can also how the model is able to represent this. So this is using a WRF model. So they try to compare how the model is able to represent this kind of different rain types. So also the vertical structure of reflectivity can be seen here for different rain types for convective and stratiform mixed. So you can see there's a wide variation in the composite reflectivity. So if you want to look at the vertical profiles, so even though they are not zenith pointing, but sorry. So are you able to see? Are you able to see this slide?
Yes, sir.
Okay. So this gives the quasi-vertical profiles, even though it makes a scan, but you can take the zenith, close to zenith profiles are constructed here to look at the vertical profiles of polarimetric data here. The top panel shows the horizontal radar reflectivity from horizontal polarization, and this is the differential reflectivity, and this is the correlation coefficient between H and B. So you can see clearly the well-defined structure of melting layer in stratiform clouds, which is, you can see the elevated horizontal reflectivity and ZDR and lower rho HV. So such high resolution representations of the melting layer with undulations could be seen in this vertical structure. Also, you can look at this during extreme rainfall event time, how the melting layer gets variations. So these are all used to study the vertical structure of these polarimetric variables could be used to study the different precipitation processes like collision coalescence or ice processes. This could be studied. Okay. So then you can also study the microphysical characteristics of a hailstorm. So using the radar data sets. So in this case, the storm extended up to Trapa Pass, 16 kilometer. So what you are seeing here, it's the hydrometeor, different hydrometeors. So rain, hail class. So all these, the frequency of occurrence of different hydrometeors could be studied. So in this case, above 4 kilometer, you can see the mixed phase hydrometeors like aggregates and wet snow and graupel and hail, which are abundant in this cell. Whereas below 4 kilometer, you can see the raindrops are like 80 to 90%, and the contribution of wet hail or graupel is about 10%. Say above 11 kilometer, you can see the occurrence of ice and ice crystals. Now, so as I started in the beginning, single frequency radar will not be able to observe both precipitating and non-precipitating clouds. So centimeter wavelength radars like the C-band, S-band, even X-band are good for detecting and deriving precipitation, whereas we need more sensitive millimeter wavelength radars to detect and map the structures of non-precipitating non-precipitating clouds. So these are some cloud radars, which Department of Energy in US armed sites use both W-band, K-band radars. So they are zenith pointing radars. So simply they look at zenith and it can observe the cloud characteristics when the clouds pass over the radar. So if you look at this, the time temporal variation, so this is the reflectivity and this is the Doppler velocity. So you can study the vertical structure of clouds. So what you see here is the lower reflectivity above the ice clouds because ice has a lower dielectric constant. So you can see the high reflectivity over precipitating regions. So there will be attenuation, large attenuation, but you can study during non-precipitating time, you can study the cloud structures. And it can give you the fraction of low clouds, middle clouds, and high clouds. So these are some of the technical parameters of these W-band. These are scanning radar. So what I've shown is a zenith pointing radar. This is scanning radars. It can also look at the spatial distribution. Even though this attenuation is the high in this frequency, so it will not be able to detect for longer ranges. I will show some results from our cloud radar, which typically can see up to 25 kilometers. And especially if you look at the sensitivity, these cloud radars have high sensitivity, like minus 20 to minus 25 dBc at 5 kilometers. So scanning radars, cloud radars can observe 3D, three-dimensional volumes of non-precipitating clouds. So starting from boundary layer cloud to cirrus clouds. So it can give you the information of three-dimensional volumes. So this is some radar observation, cloud radar observations from our site. So this 0 is our radar location, and it can scan both sides about 25 kilometers. So it can give you the cloud structure and the radial velocity and spectral width and signal to noise ratio. So with this, you can study the cloud microphysical structure. So whereas if you see the X-band at same time, if you look at the X-band reflectivity, you will not be able to see such a micro structures in X-band. So you can see the difference between X and K band radar reflectivities. And this is one of the thunderstorm which is very close to the radar site. It's about a few kilometers away. So you can see clearly the very huge thunderstorm, and you can see the updrafts and downdrafts in the other side of the storm. So the polarimetric variables also will be able to give details about the bright band structure and other hydrometeor. So still the hydrometeor distribution retrieval is still on a research topic. So people are currently working on it. So these are some scanning type cloud radar, which are put on a 20 feet sea container. And if you look at, there'll be like a non-meteorological targets like insects, because it is in the high frequency. So there could be interference from insects also. So we need to, you can screen the data and remove the non-meteorological echoes from cloud radar return. So the cloud radars, for calibration, we use reflector, corner reflector at certain distance from the radar with a known reflectivity so that the radar could be calibrated periodically. In addition, that there could be solar scan to fix the true north, etc. So these are some examples of how the data is, screened to remove the echoes from non-meteorological targets such as insects and all. And this is the typical RHI scan of a deep convective cloud system. These are some examples of scanning cloud radar capability. So now I am coming to the end of my lecture that I'll cover. It was mentioned in the introduction that we are currently working on developing a radar network. So we initially started with a mesonet of rain gauges spreading about more than 100 rain gauges in Bombay or Mumbai. Also, we are setting up a radar network to get high resolution temporal and spatial rainfall over Mumbai region, because so this will be used for flood warning system and mainly for disaster management departments, and also for nowcasting applications, so we can give information to the concerned authorities. Generally, the operational radars, they are of, it needs a huge infrastructure to set up, and also it has the problem that it cannot see when you go to larger ranges. It will not be able to see the rainfall intensity close to surface. So alternately, the small radar network is in use nowadays. I think many of the metropolitan regions are started having such a urban radar networks, because so we can use a short range small radars which could be installed in any of these buildings, existing buildings, and we can see such metropolitan regions have big skyscraper buildings. So one radar is unable to look at all the regions. So also we can put it in fast scanning. They are low cost and low maintenance. So these are the 4 different locations where 4 expand short range 60-kilometer range radars are being installed. So they are put in different regions in Mumbai. I'll show you here. So this is the complete map of Mumbai metropolitan region. So one is in south, near Panvel. The other one is in Vile Parle in Mumbai. I think those who are not familiar with Mumbai will not be able to understand. So there are several municipal corporations in Mumbai metropolitan regions. So all these 4 radars are kept in different regions. Currently, the test and site acceptance and tests are going on. So physical installation was over, and we have been currently working on data quality and data before site acceptance tests. So we are looking at the data retrieval quality, etc. So soon, I think this will be operational so that we will have a better rainfall mapping over Mumbai metropolitan region. So to summarize, I'd say the radar plays a major role in understanding cloud and precipitation processes. So I think we need more people who are trained in radar meteorology. So it's not only here. I think the several other metropolitan cities are also will be getting such urban radar networks in coming years. And the National Weather Service, India Meteorological Department is also augmenting radars. And I think there'll be many radars will be coming in not only in India, maybe in other developing other countries also. So I think this course is will give a good good insights to those who are coming into this field, which will enlighten the people. And I think the centers like ACARR and IMD and ISRO. So many agencies are using MOES, all are using the weather radars in India. Similar may be the case in other countries also. And we need many more radar engineers, radar scientists, and radar meteorologists in coming years. So I think this will give an opportunity for better platform to these youngsters who are entering into this field. So with this, I'll stop here and we'll be happy to take the questions. Thank you.
Sir, we will have a photo session.
Okay.
So please stop sharing.
Sure.
Request everybody to switch on their camera. And one more. One more person I to Andrew and Savas.
Shall I start?
Just a minute.
Got one more person. Is he from CUSAT? Andrew?
No.
No?
We can have it.
Okay.
Yes.
Okay, done.
Thank you.
Okay, now we'll have the Q&A session.
Okay. Thank you, sir. The first question is, which algorithm to use for the calibration of radar data using point measurements?
Point measurements of which algorithm? There is no I cannot say so and so algorithm is available, but so if the rainfall measured from the ground station is we are sure that it is good, so we can use this as a ground truth and adjust the radar derived rainfall. That's what I will say.
Okay, sir. Thank you. And the next question is, how is CPR data integrated with the other meteorological data to enhance weather prediction models?
CPR, you mean cloud profiling radar? If it is so, as of now, the cloud profiling radars are not going into weather prediction models as of now. So it is still in the research mode to understand the cloud processes and improve the parameterization scheme. Then it will go into the models. So that's what current status.
Okay, thank you, sir. Another participant is asking to discuss more about convective clustering concept and what are its advantages.
Okay, so see, convective clustering is that initially the convection starts like here and there scattered convective cells, and then it gets, if the convective cells are slightly bigger, then it can gets organized. So there are some indices like convective standard convective clustering index. So there are some indices for this. So which is a function of the size of the convective cell and the distance between the two cells. So using that, we can see that we can study what is the probability of getting the clusters more, because if the interdependence between two cells are more, so it's a less probability. There are indices for that.
Okay, sir. The next question is, what are the primary applications of cloud and precipitation radar in meteorology and climate research?
Can you repeat? What is it?
What are the primary applications of cloud and precipitation radar in meteorology and climate research?
Yeah, so the precipitation radars are used to for cyclone warning applications. So they are long distance radar like S-band radars. So they are put in coastal regions. So it can see up to 400 kilometer for cyclone warning applications and surface rain intensity mapping. And also to see the movement of precipitating systems, so that you can nowcast on what direction it's going to the heavy rainfall or the convective storms are moving. So mainly used for rainfall intensity and cyclone detection and rainfall nowcasting systems. Cloud radars are still in the research stage. People are using to study the vertical profiles of clouds, so that it could be used in the parameterization development.
Thank you, sir. And another question is, how to become an expert in radar meteorology? One question is from participant. There's some courses and yeah,
you are in a right platform that you are attending this course and also can explore other. So then there are it's a radar meteorology you are saying. So it's kind of science. If you want to be a radar engineer, so you need to study the engineering aspects. So it gives for different people engineer the option of exploring the signal processing, hardware, retrieval. Retrieval comes into the scientist mode domain. So and then there are several options that you have to go through courses, or in meteorology, you can, if you are good in meteorology, okay, you can focus on radar meteorology and become a radar meteorologist.
thank you, sir. The next question is, what advantages can we gain over studying non-precipitation clouds using radars?
Yeah, so the precipitation radars will be only seeing the precipitating clouds, because it's it is in centimeter wavelength. That's what the interaction between the radiation and the target, the scattering depends on the wavelength of the radiation. And non-precipitating clouds also we need to understand, right? Because if you can only see, if a radar you have and it does not see the cloud, it only sees when it is raining. Then the raining clouds only you can see. If you want to see, I'm seeing the sky, seeing the cloud, but radar is not showing anything because it's not sensitive, because it's in centimeter wavelength. So we need to understand the climatology, because people may be knowing that there is a cloud climatology project. So we need to have the statistics of what fraction of clouds are low clouds, middle level clouds, and ice clouds. For all these studies, we need to have a non-precipitating cloud observing system. That's why cloud radar comes into play.
Thank you, sir. The next question is, how can we quantify the columnar precipitational water in CB?
Columnar precipitation. Okay, anyway, the radar gives a volume of volume structures. So how we are integrating, we can integrate it with with the column, so you can get the column integrated rainfall.
Okay, sir. Next is there any way to give a certain way to warn cloudburst events? Some early warning for cloudburst, he wants to know.
Yeah, that's what. So if we have, see, all these cloudbursts are mainly happening in the orographic regions. So in the orographic regions, if we have good radar coverage, so we'll be able to see and give a nowcasting warning. So sometimes heavy precipitating events happens, develops and pours in few hours. So that could be nowcasted using radar. Good coverage of radar networks. So we have radar, but if it is not seeing that region, so I think sometimes even in the plains, you have problem. But I think in the orographic mountainous regions, if we have a cloud radar, so which will help to give some information on nowcasting the cloudburst events.
Thank you, sir. Next question is, please provide a way to peek into the gust front or sea breeze front.
I'm not very familiar with this area because I think it maybe must have dealt by aviation course during this. Maybe we can look at that course again to look at the gust front applications.
Yes, sir. The next question is CPR being used to improve disaster preparedness and response?
No, I think CPR is cloud profiling radar generally used for, it has a very low range, it has high attenuation. So it is mainly on research as a research tool. So mainly to study.
Okay, sir. Next question is, how efficient the radars in forecasting extreme precipitation on spatially?
Can you tell again, please?
How efficient the radars in forecasting extreme rainfall?
Yeah. See, radar cannot give a forecast. First of all, I think people have to understand radar data sets can, so at the most it can be used as an outcasting information. So it's not, actually the models will give the forecasting because it has memory and it can give, but radars cannot give a forecast, but it can give an information on outcasting few hours before.
Thank you, sir. One participant is asking to discuss about the details of advanced studies or courses regarding radar subjects offered in overseas. If some sort of information or courses he can do.
Maybe he can keep watching. There are European radar conferences. Before the conferences, they can have some courses. So generally, they will have some courses. Even we are going to have India Radar Meteorology Conference in Mumbai in coming January. So even before that conference, we are going to have one-day school. And we are also planning to have in IITM some radar school. Sometimes that I can circulate once we finalize that. Overseas, I think people keep watching this. I think there are many conferences wherein they may have before the conference few days of school.
Sir, there is one question in YouTube. Sir, when we are placing so much instruments in one hub like ART-CI, how to top issues of interference and tackle the issues of interference and different instruments from different instruments?
What type of interference? Because generally we keep, because it's a very huge area. So we are keeping strategically, okay, so this should not affect this, this should not affect this. And they are working in different frequency regimes. Some are scanning, but anyway, radars are working in narrow frequency. So, all these instruments are deployed in 100 acres of land. So they are deployed in different regions of this facility. So other than microwave interference, so there are different frequencies we are using. So some are zenith pointing, some are scanning. So we don't
Thank
see.
you, sir. Yeah. So that's all from YouTube and this question and answer session here. So over to Dr. Abhilas.
Thank you, Millie Madam, for handling the Q&A session. Now I request Someshwar sir to speak some words.
Okay, thank you very much, Dr. Pandithurai, for a very interesting lecture. And as it was said in the beginning, Dr. Pandithurai is not only a very good scientist, but also a good teacher. And as you have heard his lecture today, he has explained such a complex subject in such a simple way and very interesting manner. So I hope all of you have benefited. You can go through the YouTube lecture, which will be archived on the YouTube channel of Sama. If many things are not clear to you, then you can just go through the lectures again and again. And it's very interesting to see that a lot of questions raised by the participants on various topics. And so that shows that people are really attentively hearing lecture and also quite interested. If somebody wants to become a radar meteorologist, so it's very good. Yes, why not? Definitely, if you have the interest, you can become the radar meteorologist, certainly. And it's a very important subject as well, because there was so much of applications in so many areas, and especially as Dr. Pandithurai has said that, particularly this cloud radar, etc., are very, very important for retrieval of the cloud microphysical parameters, which are very important for doing research on the cloud microphysics. And as you may be knowing that in almost all the numerical weather prediction models, we have got the cloud microphysics parameterization. So many of those parameterization schemes are approximated because when we use the scheme at the scale of the NWP, which is normally a few kilometers, sometimes 5 to 10 kilometers, whereas the cloud microphysical processes, they operate at micro levels. And so therefore, NWP models are certainly not capable of resolving the cloud microphysical processes, and therefore such things can be observed through radar, and then whatever you obtain the results from the NWP or the cloud microphysics scheme, then those things can be verified with each other and then improved. The scheme can be improved accordingly. So a lot of scopes for all these things, cloud radars, precipitation radars, and there are many more kinds of radars that you have heard in the last 10 lectures. So keep studying all those materials, and certainly one day, if you continue to be interested, you will definitely become a good radar meteorologist. And as Dr. Pandithurai has mentioned that, see, the radars are instruments. They are not models to predict. They can give you the instantaneous values, the current weather system. At most, it can give you the nowcasting for the next 2-3 hours based upon the movement of the cloud systems as observed by the radar. But if you want the prediction, like the cloud burst, then you have to have a model. And a good model will not only use the radar observations, but also the satellite observations and many more types of observations, because it's like predicting the evolution of the atmosphere. And that too, if you're thinking of using this to predict the cloud burst over the mountains, mountains have another complication because they block the radar beam. So the radars have to be of a special wavelength. Like most of the mountainous areas, we have generally the X-band radars because it has got short range. You can't have a S-band or even C-band on mountains because the beam should be blocked. So you have to have a good network of X-band radars over mountains. And a lot of things are there. Therefore, not just the radar, but also the satellites as well as many other things are required for the forecasting of extreme precipitation. Somebody was asking whether it can be used for forecasting extreme precipitation. Yes, but not standalone. It has to be used in combination with other instrumentation. Somebody was asking whether it can be used for studying the gust front. And what is gust front? And if you have heard the terminology gust front, then you should know also what is the gust front. See, I mean, it's just a wind, basically, right? The variation of the wind. And for that, you have to have not just a radar, precipitation radar, but you have to have profilers, wind profilers. There's many types of wind profilers available: boundary layer, wind profilers, mid-tropospheric, tropospheric, mesospheric, and so many things. So you have to have a proper instrumentation to study the cloud gust fronts, especially which are associated with the thunderstorms over the airport. Particularly, they are very important for landing and taking of the aircrafts. Therefore, you have to have appropriate instrumentations for that. So certainly, it was a very interesting lecture. Thank you once again, Dr. Pandithurai, for a nice lecture.
Thank you.
Yeah, thank you.
Thank you so much, sir. Now I invite Ajit Syagi sir to speak some words.
I think thanks to Pandithurai for making such a complex subject so interesting, and positively you have been able to create interest among many of the participants. And Somesh has summed up the importance and the application of these technologies which are emerging now. Continue to, you see, the amount of radars going to be in the country, we could not dream earlier that yes, there will be radars from S-band to the cloud radars and the urban radars, and so all this is great opportunity now for all of you to use these radars for your studies, research, application, and improve. And you see, another important thing is that there is nothing universal about that. There, of course, the science is universal, but the application, or the orography, or the plains, or the coastal areas, we have to work out how these radars are really working and what all algorithms which needs to develop for these regions have to be worked out. So there are a lot of opportunities. And, once again, thank you, Dr. Pandithurai, and of course, I'm happy that participants are taking keen interest. Thank you.
Thank you, sir. Now it's time for vote of thanks. I request Dr. Paulami Chakravarti madam to deliver the vote of thanks.
Sure, Rakesh sir. I'll quickly share my screen if that's okay. Esteemed guests, distinguished speaker, and respected colleagues, as we conclude the 12th lecture of the Radar Meteorology Lecture Series, it is my honor to extend the vote of thanks on the behalf of the South Asian Meteorological Association and the Advanced Center for Atmospheric Radar Research at the Cochin University of Science and Technology. Firstly, I express our gratitude to Professor Someshwar Das sir, Secretary of SAMA, for his vibrant welcome address that set the precedent for the lecture. We also extend our heartfelt gratitude to Air Vice Marshal, retired Professor Dr. Ajit Tyagi sir, President of SAMA, for his inspiring opening remarks and unwavering dedication to guiding the youth of our generation with your tireless efforts. We would also like to express our sincere commendation and gratitude to our eminent speaker today, Dr. G. Pandithurai sir, who is a scientist G at the Project Director, Atmospheric Research Testbeds at the IITM Pune, India, for your enlightening lecture on cloud and precipitation radars. We also deeply appreciate Mr. Rejoy Ribello, engineer at the ACARR, Cochin University of Science and Technology, for the eloquent introduction conveyed by him for our guest speaker today. We are deeply appreciative of Dr. Millie Ghosh Nilala, who is an assistant professor from BIT Mesra, India, and also an ECT member of SAMA, for her efforts on moderating the question and answer session and making it a lively and productive discussion. Along with that, we express our heartfelt gratitude to Dr. Abhilash as Director of the ACARR CUSAT and the program convener for the Radar Meteorology Lecture Series for overseeing the entire session and seamlessly orchestrating the Radar Meteorology Lecture Series. Lastly, I would like to thank all the participants for their active engagement and contributions. Once again, thank you all present today and those working on the sidelines for making this session a success. Have a great day, everyone.
Thank you, Paulami madam, for delivering the vote of thanks. Now we will end up the session, and the next lecture will be on 31st August by Dr. Soma Sen Roy on DWR utilization in nowcasting. So we will meet on that day.
Yeah, thank you very much. Let me thank Dr. Tyagi for his kind words and all SAMA executive committee members. Dr. Someshwar Das, and all members. Thank you very much for coordinating this. Thank you.
Thank
Thanks.
you.
Bye.
Please stop the YouTube live stream.
I think Divya is on there.
Okay, we will inform you.